okay, I had a brilliant last movie all done and everything, and then I'm in a hurry. It's happy hour. It's Miller time or whatever. I mean, if you can drink that stuff, but I'm not one of those, real, snooty people who go, oh, I won't, I need to have a whatever IPA. Yeah, if it's 9%, bring it on. No, but anyway, yeah, because every once in a while, a good, as I call it, Union beer, it just tastes good. A good old Miller or my favorite Rolling Rock, which my son-in-law just can't stand. Like, hey, at 50 cents a beer, you know what I'm saying? No, I'm promoting bad things. So anyway, I had this all done, and then I accidentally turned it off. So let's review the bidding, because now we're going to figure out how far would Michaela go if she's at the bottom of the hill and whisking along, and she hits the bottom of the hill at 18 meters per second, almost 40 miles an hour, hits choppy, icy, crunchy snow, had a coefficient of kinetic friction of 0.15, and we computed the force of the frictional force is negative 88.2 newtons. So that's a lot of stuff. Let's review the bidding. Here she is coming down the hill. All right. On her skis. Now she's got a velocity going this way of 18 meters per second, and the only force that's acting on her, I mean, we're going to get to drag in 7.2, is this force, this kinetic frictional force, which we computed was 88.2 newtons. All right, that's its magnitude. But look which direction that's going. It's going negative. We also found that her change in kinetic energy was equal to negative 8970 joules. Okay, now, do you remember the good old work is equal to force times distance? Yes! So we got this. So our force, though, is negative F of k, because it's pointing to the left, times the distance is equal to, now this is what messes students up all the time, especially when they're new to fix it. They're like, what, 3? You've got 3 equal signs? Yes, because work is equal to force times distance. It's also, which is here, it's also equal to the change in kinetic energy, which is 8970 joules. So now I know how far she went. I can calculate how far she went. So look what happens. Negative F of k times d, and she went is equal to negative 8970 joules. Negative 88.2 times d is equal to negative 8970 joules. Okay? D is equal to, divide that, and I already did, but I'll do it again. So here it is. It's divided, negative 8970, and we get 99 points. Let's go at 99.7 meters. Almost 100 meters. It's like you better put up some barrier. Oh, Michaela, she's down in the parking lot now. And if she came down the hill at her normal speed, let's say at her super G speed, and she hit the bottom of the hill and didn't do her nice little turn and stuff, and just kept going straight, she'd be in Denver by now, especially with the snow the way it is. But she likes to train in the East Coast. So you guys see how this is done? It's not that hard. Look at all we did with just a few things. All we knew was her mass and her starting velocity. And look at all the stuff we came up with. Of course, I was making up stuff as we went along, like what was kinetic. We had a lot of, and we had the coefficient of kinetic friction. But that's all, we just needed those 3 pieces of information, and we came up with all kinds of stuff. Now, usually what do people do in an investigation or like say she got hurt and they wanted to know, well, how fast was she going and da-da-da-da. What they would do is they would analyze all this stuff and come up with, oh, well, this is her math, this is how far she went, and do it backwards. And go, oh my gosh, she hit this at this speed and she can't do it, she can't go that fast. All right, you guys are going to do this on your own now. And what you're going to do is you're going to do a big ass bobsled coming down, which is fine. It's just a lot bigger than Michaela. All right, that's all. It's just got more mass. It might be going faster, and the snow might be more crunchy. And it's going to come to a stop after going really, because those bobsleds get up to 90 miles an hour. whooshing around, and we're going to say, we're not going to look at the braking force, but we're just going to look at the if there was no brakes, how far would it go with if they didn't brake it and just counted on the frictional force? All right, so out here.